So I want to look at this problem subsets. It says given an integer array nums, return all possible subsets. So it can be in any order, and a subset is just in any combination of the elements in any particular order. And there are multiple ways to solve this, but I want to look at the bit manipulation solution, the bit masking solution. Not necessarily because bit manipulation is all that common of a tool that you'll need, but I think bit manipulation is one of the best, if not the best, pure examples of how to apply a pattern in ways that you're not used to. And this problem is a great way to do that. And what I mean by that is, I think we sort of have multiple types of tools when we approach these problems. How you approach this could involve, hey, I know how to do a depth first search and backtracking, or hey, I know this specific method in Python that gives me this anyway, so maybe I can do a one-liner just with a built-in function. There's different tangible tools like that, and I think there's also different, more intangible tools, more abstract tools that we have, such as, hey, I don't know a method that just gives me this, or I don't know how to do backtracking. Can I hack it? Can I figure it out on the spot? And if you're ever in an interview, obviously it's optimal to just already know the answer to everything, but I think there's a much more valuable skill, and I think most interviewers can pick up on it, that's how well can you think on your feet? How well do you do when there isn't just already a laid out answer that you happen to know? And I think bit manipulation's in an interesting spot because it's pretty rare that you need bit manipulation as the tool itself, but it's one of the more common tools that you wind up applying indirectly. And where I'm going with this is, I think that behavior of matching patterns and going, hey, this sort of seems like that. Maybe if I don't know the answer, maybe I can sort of create this, some sort of dialectical answer by combining two things that I wouldn't normally combine. So let's hop into it. Let's look first at these test cases. So we see 1, 2, 3 has a set of none of them, a set of 1, a set of 2, a set of 1 and 2, a set of 3, and so on. So if we're thinking about how do we obtain these sets, how do we represent these sets, really is almost exactly the same way of, that's almost the same statement or question. We can think of these as sort of binary arrays. So for example, let's take none. This would be a binary array of all false. We say, do we include 1? No. Do we include 2? No. Do we include 3? No. And then for the set that just contains the number 1, we say, yeah, we do include the number 1. We don't include the number 2, we don't include the number 3. And I should clarify here, we're using 1s and 0s to represent trues and falses. For 2, we say we don't include the 1, we do include the 2, and so on. And then for 1, 2, and 3, it's all 1s. The set that is what we're given is always going to be all 1s. So if we look at this, we can sort of start to see a pattern, and it's that these are pretty easily represented by numbers. Not only do these represent the sets as a binary array, these binary arrays also, in this specific order that they even give us in the example output, they say return it in any order, but they return it in a specific order. And if we look at that, the order actually represents counting 0 through 7 for the 7 subsets. So the set of none, 0, 0, 0, if we look at this in binary, 0, 0, 0, that's 0. And then let's flip it, because it's sort of the same, doesn't really matter, but it makes it simpler. If we say, okay, this is sort of 0, 0, 1, that's 1, and then 2 and 3 up to 7 is going to be all 1s. And if you think about it, we're always going to start, no matter if this is, let's say, 1, 2, 3, 4, 5, 100. Very sloppy. Okay, fine. Those could be the same. So we have 1, 2, 3, 45, 100. This will always still, if we arrange it in this order and we represent it with these binary arrays, it'll always start with a bunch of zeros. So the first thing we would look at is 0, 0, 0, 0, 0, with all the commas. And then the last thing we would look at is 1, 1, 1, 1, 1, with all the commas. This representing the set of none of these, this representing the set of all of these. And then we could just count up. So we would say 1, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, and so on. And something we notice is, okay, we're starting at, if we choose to again represent this binary array as a number, it always starts with 0 and it always ends with a bunch of 1s, which means this is just below the next power of 2. So this would be 1 plus 2 plus 4 plus 8 plus 16 is going to be 31. So here we need to count up 0 through 31. And here we're counting up 0 through 7 to represent all of these. And that really is, I think, the most important thing here that I'm looking at is that a number is just a binary array without the fluff. It doesn't have a length property. It doesn't have a type of elements property or whatever that arrays typically have built in. A number is a binary array with no fluff whatsoever. It's truly a bunch of 1s and 0s. And I guess it has you have one wasted bit that's whether or not it's negative. But yeah, so if we paste this solution, let's look through how it works. So we have, it's good to often define n in these at the beginning. I find I mostly do that because it helps looking at big O notation later on. You can say, oh, this is how n was used, so O of n would be blank. So then we go on to define cap, which is going to be 2 to the n. So here, n is going to be 3, because we're looking at the example 1, 2, 3. And cap is going to be 8. So then we make our answer, and we say, okay, for mask in range cap, so we're saying, you could say this is for I in range cap, but mask is a little more verbose. So it's saying iterate 0 through up to 8, so 0 to 7, which works out super neatly, because 0 up to 7 is exactly this. And if it was this, n would be 5, cap would be 2 to the 5th, so 32, so this would be 0 through 31. So this is an extremely efficient line to basically say, hey, in number form, so we have to sort of turn it into a binary array or parse through it somehow, but in number form, give us every single combination we want. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1. Or sorry, 1, 1, 0, 1, 1. Get the current, and then here we have a little bit of, this is where the bit manipulation is explicit. We say for bit in range n, because we know that n not only is the length of nums, it's the length of mask in a way, because mask is going to be a bunch of 1s and 0s, and all we care about is the first, in this case, 3 1s and 0s. So whatever mask is going to be 0 through 7, it's going to be only 0s past the 1s place, the 2s place, and the 4s place, aka the first 3 digits in binary. So then we say if 1 bit shifted to bit, which just means if bit is 1, then, or if bit is 0, then we're saying if 1. If bit is 1, then we're saying if 2. If bit is 2, then we're saying if 4. So we could rewrite this differently and say 2 to the bit minus 1. But bit shifting is a lot faster than exponentiation. So, because the computer can do this almost instantly with saying something like power. In fact, if I was being very efficient, I could change this to a bit shift. But something like power, the problem is this could be 3 to the n, and then they can't really just do any simple binary trick of just shifting over all the bits by 1 and parsing it that way. But anyway, if one bit shifted to the bit and mask, so what we're doing here is we're going through and we're saying, okay, let's take this one, 110. So for bit in range n, for bit in range of 3, we're saying if 1 bit shifted to the bit. So for the first iteration, we're saying, hey, if this and mask, where this is our mask, which is false, cur.append nums at bit. So it's saying append the 0th element. So here, again, this is flipped, but I would say ignore that because it's not all that worth looking into. It's just more confusing than or it's counterintuitive, but it doesn't really add anything to think about it. We're saying, okay, this one's false. And then the next iteration of for bit, we're saying, okay, bit shift over 1. Now we're looking at the 1's place in, what is this, 6 is the number that represents this binary array. That is true. So when we look at the 1's place, we could say, okay, yeah, include this. And bit now is 1. So we say, take the first element, or again, the n minus the first element, but whatever, and include that in current. So cur.append nums at bit. And then do the same thing for this one, which is going to be true because it's a 1. So append that. So for 110, we're appending 1 and 2. And then we just iterate through every single thing. So if we say, for example, mask is 0, what we're going to do is we're going to say, okay, cool, current is a new list. For bit in range of n, so we're going to iterate through 3 times. If 1 bit shifted to bit and mask, then append a new thing. But mask is 0. So mask will, anything and 0 will always just return false. So this will always return false. Nothing will get added to cur. And then we append an empty list, which is exactly what we want. And then if we take the opposite case, we say, okay, what if current is what if mask is the last thing? So cap minus 1, which here is 7, we say, okay, cool, cur is a new list. For bit in range of n, if 1 bit shifted to bit and mask is all 1s here, at least for in the range of n, all that we care about. So it's going to be 1, 1, 1. So we're going to check 0, 0, 1 and 1, 1, 1 is going to return true because that evaluates to 1. 0, 1, 0 and 1, 1, 1 is going to return true because that evaluates to 2. And at least in Python, and I think in almost every language, 0 evaluates to false for a number, and anything other than 0, positive or negative, evaluates to true. But anyway, 1 bit shifted to 2, and 1, 1, 1 is going to evaluate to true. And 1 bit shifted to 3, or sorry, a 1 in the 3's place, and 1, 1, 1 is going to evaluate to true. So it's going to add everything because they're all 1s. Yeah. So we could see in the end too, we can maybe put a print statement in here and say print cur, and when we run it, we can see it's going in this very specific order: 0, 1, 2, 3, 4, 5, 6, 7, and we can even explicitly state that. We could say print cur and mask. So we should see 0, or let's do it the other way because the length of cur changes. So we can see 0, 1, 2, 3, 4, 5, 6, 7. And if you ignore these elements, if you just think of them as, let's say, 1s, we can kind of see like, oh yeah, I guess the number 0 doesn't have any 1s. The number 1 has a 1 bit, and the rest of them are 0 bits. 2 has a 1 bit, and the rest of them are 0 bits. 3 is 1, 1. 4 is 1, 0, 0. 5 is 1, 1, 0, and so on. Yeah. Or sorry, 1, 0, 1. And if we add a couple elements, let's say 4, 5, 6, 7, 8, 9, 10, because nums.length is going to be less than or equal to 10. We should see this goes up to 1024. It prints up to 1024 because we have to evaluate 2 to the 10th different possible sets. So when we look at cap, we say, okay, n is 10, cap is 2 to the power of 10, which is 1024, and then we're in range 0 to 1023. So in the end, if we print length of answer, and let's just comment that out for now, we should see 1024, because we're iterating through 0 to 1023, and then we include the 0th element. But let's go back to this one. We can see, okay, this is our number representation of the current set. So if we scroll down to a random point, let's go to 512, because that should have one element. Because what this is this is saying, this is 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. So this is only going to contain 10. And then we can see, oh, 513, that's, sorry, I included a 0 in the beginning there. It's 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. And we can see, hey, that one includes the last element and the first element, and then the last element and the second element, and then the last element and the first and second, and so on. So if we look right here, if we compare this to everything before it, we can see, hey, just like with numbers represented in binary, all of these sets, where are we at? All of these sets, 5, 12, and after, are the exact same as all of the sets above, just including the 10. So if we scroll down to the very bottom, we'll probably see, hey, 511 is 1, 2, 3, 4, 5, 6, 7, 8, 9. The very last one is probably, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because it's, instead of being 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, it's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Yeah. So I think the utility in this problem isn't necessarily in optimization. I think this is pretty heavily optimized for memory because you're only using ints. But if we look, it's not the fastest. And this happens to be the fastest runtime I've gotten. Because it's a Sunday, so not a lot of people are doing this. But we can see it varies pretty widely. And a depth first search here is a little faster, I think, on average. So that's not really the utility here. We're not necessarily using, I'm not insisting on using this integer notation because it's the most optimal way to do this. I'm insisting on using integer notation, or I've chosen to use integer notation because it's an extremely good exercise in applying a pattern, bit manipulation, and noticing that integers are binary arrays, essentially, of true and false numbers. It's a really good exercise in doing that and finding a solution to an answer that makes no mention of bit manipulation or any of that in any way. And the more that you can do that, the more that you're setting yourself up to think quickly on your feet and find solutions to things that do not already have solutions that you've memorized. And I think that's one of the most useful skills you can have.